Good morning all. In last days we have learned about rings. A ring is an algebraic structure R plus dot, where R is a non-empty set, plus and dot are two binary operations on it, and with it satisfies three axioms. First one is R plus is an abelian group. With respect to multiplication it is an associative, and R3 is it satisfies the distribution laws, left and right distributive laws, and we have learned about we have seen some examples. Also we have learned some characteristics of rings and homomorphisms and isomorphisms of rings. Today we have some special types of rings. Three types of rings are to be studied. First one is commutative rings, second one ring with unity, and third one the division ring or skew field. We have already R plus is an abelian group. With respect to multiplication, the group property, only associative property is satisfied. The next property or one more property, the commutativity. If commutativity is there, it is called commutative ring, and if unity, with respect to multiplication, the identity is there, then it is called ring with unity. Like that, we can move to the portions. So we have special types of rings. First one, commutative ring. A ring R in which the multiplicative composition is commutative, that is AB equal to BA for all A comma B element of R is called a commutative ring. A ring also with the property with respect to multiplication it is commutative, that is called commutative ring. With respect to addition, the R is an abelian group. Now we have to check an additional conditions of the group property in multiplication. So first we are checking the commutativity property. If it is commutative, the ring is called commutative ring. For example, the set Z, the set of integers, R, the set of real numbers, C, set of complex numbers, Q, set of rational numbers. With respect to ordinary and addition and multiplication is a commutative ring. There, with respect to multiplication, we have the property AB equal to BA. The set of numbers in the form A plus B root 2, where A comma B element of R forms a commutative ring with respect to ordinary addition and multiplication. We have already seen that it's a ring. Now we have to check whether it is commutative. The A plus B root 2 into C plus D root 2. We will get the same answer as C plus D root 2 into A plus B root 2. That's the answer. And we have a counter ring which is not commutative. An example for that is MNR, where R is a ring and the MNR is the collection of all n by n matrices, is not a commutative ring with respect to addition and multiplication. Matrix addition and multiplication, we know that matrix multiplication AB not equal to BA, so it is not a commutative ring. So commutativity property should hold to be for a ring, then it is called commutative ring. And the ordinary groups rings Z, R, C, Q all are rings with commutative property holds, so it is commutative rings. And MNR, the matrices group with n by n matrices group ring is not commutative. Next we have ring with unity, that is a ring, there is a ring and we have the multiplicative inverse. If it is there, then it is called ring with unity. If in a ring there exists a multiplicative identity, that is an element denoted by 1 such that 1A equal to A, which is equal to A into 1 for all A element of R, is called a ring with unity. For example, the set Z, the set of integers, R, the set of real numbers, Q, the rational numbers, C, the complex numbers. With respect to ordinary addition and multiplication is a ring with unity. There the unit element 1 is there with respect to multiplication, 1 into some a is equal to a, which is equal to 81, any number into 1. Now the set of numbers in the form a plus b root 2 again forms a commutative ring with respect to ordinary addition and multiplication. Here also the unit element is 1. Now m and r, where r is a ring, is also a ring with unity. Here the unit element is the identity matrix in, not the set E of even integers. Even integers 0, 2, 4, 6 ആണ് പോവുക. അവിടെ the numbers is, the 1 is not there, so it's not a ring with unity. And the set n is set of integral multiples of integers, of ആണ് ഓടല്ല, of integral multiples of integers with respect to ordinary addition and multiplication is not a ring with unity. Now we have 0 and unity of the ring. The additive identity element 0 of a ring is called the 0 of the ring, and the multiplicative identity element 1 of a ring is called the unity of the ring. With respect to addition, 1 identity element is there, it is called 0, and with respect to multiplication, 1 identity element is there, it is called unity. Now we have the next type of special ring, division ring. Let R be a ring with unity 1 not equal to 0. An element A in R is called unit of R if it has a multiplicative inverse in R. If every non-zero element of R is a unit, then R is a division ring or skew field. With every non-zero element, then the inverse, if its inverse exists, with respect to multiplication its inverse exists, then it is called the division ring. Thus a ring R with at least 2 elements is called a division ring if the non-zero elements of R form a group with respect to multiplication. That is, a ring R is a division ring if it has at least 2 elements and has unity such that every non-zero element has a multiplicative inverse in R. Now we have examples of division ring. The set of real numbers, rational numbers and complex numbers with respect to ordinary addition and multiplication are division rings. Now the first condition of division ring is it should be a ring with unity. Therefore the set of E of integers and the set of NZ of integral multiples of integers with respect to ordinary addition and multiplication is not a division ring, since they are not ring with unity. Also, the ring of integers, the set of numbers in the form a plus b root 2, where a comma b element of R forms a commutative ring with respect to ordinary and multiplication, and M and R, where R is a ring, the collection of all n by n matrices, are not division rings, since all the non-zero elements of these sets do not possess multiplicative inverse. അപ്പോൾ എല്ലാത്തിൻ്റെയും ഇൻവേഴ്സ് എക്സിസ്റ്റ് ചെയ്യുന്നില്ല. Now we have two problems. Find all the units of the following rings. First ring is Z14 and the second problem is Z cross Z. Next problem is find all units of Z14. We know that Z14 is equal to the set of all elements from 0, 1 to etc. up to 13, and the operations are addition modulo 14 and multiplication modulo 14. So this is the Z14 group. So ring, Z14 ring. So here 1 is the unity element. That is, 1 is the identity with respect to multiplication. Now 1 multiplication modulo 14 multiplication 1 is equal to 1 itself. Therefore inverse of 1 is 1 itself. Now additive inverse of 1 is, that is 1 is a unit. Now additive inverse of 1 is, additive inverse of 1 is 13, since 13 plus 1 is equal to 0. Consider 13 multiplication modulo 14, 13. Now 13 into 13 is 169. When we divided by it by 14, the remainder is 1. Therefore 13 is a unit. In Z14, for a non-zero number to be a unit, unit its multiple should be 1 more than a multiple of 14. നമ്മൾ റിമൈൻഡർ എടുത്തു കഴിഞ്ഞിട്ട് നമ്മൾ ഡിവൈഡ് 14 കൊണ്ട് ഡിവൈഡ് ചെയ്ത് കഴിയുമ്പോൾ 1 റിമൈൻഡർ 1 അതിൻ്റെ ആ സംഖ്യകളാണ് വേണ്ടത്. അപ്പോൾ അങ്ങനെ വരണമെങ്കിൽ ഇറ്റ് ഷുഡ് ബി 1 ഗ്രേറ്റർ ദാൻ ആയിട്ട് വരണം. So since each of this number 2, 4, 6, 7, 8 and 10 have a common multiple of either 2 or 7, these numbers 2 or 7 with 14, multiple of none of these numbers can be 1 more than a multiple of 14. നമ്മളിപ്പോൾ 7 എടുത്തു, 7ൻ്റെ ഏത് മൾട്ടിപ്പിൾ എടുത്തു കഴിഞ്ഞ് കഴിഞ്ഞാലും 7 into 2 it's 14. So remainder should be 14 കൊണ്ട് ഡിവൈഡ് ചെയ്യുമ്പോൾ remainder will be 0. 2 into ഏത് നമ്പർ എടുത്തു കഴിഞ്ഞാലും പ്ലസ് 1 എന്നുള്ളൊരു രീതിയിൽ വരില്ല ഒരിക്കലും. 14 plus 1, 14 into multiple plus 1 എന്നുള്ളത് വരില്ല. 2ൻ്റെ എല്ലാ മൾട്ടിപ്പിൾസും ഈവൻ നമ്പേഴ്സ് ആയിരിക്കും. അപ്പോൾ അത് റിമൈൻഡർ എടുത്തു കഴിഞ്ഞാൽ ഏതെങ്കിലും ഈവൻ നമ്പറേ കിട്ടുള്ളൂ, 1 കിട്ടില്ല. 7ൻ്റെ എടുത്തു കഴിഞ്ഞാൽ അതും കോമൺ മൾട്ടിപ്പിൾ ഉള്ളതുകൊണ്ട് 1 കിട്ടില്ല, വേറെ ഏതെങ്കിലും നമ്പർ കിട്ടും. So none of these numbers can be 1 more than a multiple of 14. Hence these numbers are not units of Z14. ഇനി നമുക്ക് ഇപ്പോൾ 1 കിട്ടി, 13 കിട്ടി. ഇനി ബാക്കിയുള്ള ഓഡ് നമ്പേഴ്സ് 7 ഇതിൽ നോക്കണ്ട, ബാക്കിയുള്ള ഓഡ് നമ്പേഴ്സാണ് നോക്കേണ്ടത്. അപ്പോൾ വി നോ ദാറ്റ് 3 into 5 is equal to which is 3 multiplication modulo 14, 5 is equal to 3 into 5 is 15. 15 14 കൊണ്ട് ഡിവൈഡ് ചെയ്ത് കഴിയുമ്പോൾ remainder is 1, which is equal to 5 into 3. Therefore 3 and 5 are inverses of each other, and hence they are units. Now additive inverse of 3 is 11. Since 3 addition modulo 14, 11 is equal to 0, and that of 5 is 5 plus 9 is equal to 14. So since 5 plus addition modulo 14, 9 is equal to 0. Consider 11 multiplication modulo 14, 9 which is equal to 99 when divided by 14, remainder is 1, which is equal to 9 addition multiplication modulo 14, 11. Therefore 11 and 9 are inverses of each other, therefore 9 and 11 are units. Therefore units of Z14 are 1, 3, 5, 9, 11 and 13. Next problem is find all units of Z cross Z. We know that Z is a ring with unity with respect to the operations. Usual addition and multiplication. Addition and multiplication. Therefore, Z cross Z is a ring with respect to the operation addition and multiplication defined by addition and multiplication defined by AB plus CD is equal to A plus C, B plus D, and ABCD multiplication is equal to AC BD, where A comma B comma C D element of Z. This is the operation in Z cross Z. Now we have to find the units of, so here the unity is, the unity in Z cross Z is 1 1. The identity element is 1 1. Now we have to find for all non-zero the inverses of each element. The element consider some n comma m element of Z cross Z, where non-zero, a non-zero element. Where n not equal to 0, m not equal to 0. For any r comma s element of Z cross Z, we have nm comma rs is equal to 1 1, which is equal to rs into, we have to find the inverses of that. So we have to find rs. Nm for every the rs, we have to find the inverses of nm. For that we have taken a non-zero element nm and take another element rs. Now we have to find this r and s. For this we have multiplication is defined as nr into time wise first coordinate nr and next coordinate is ms, which is equal to 1 1, which is equal to Rn ms, which implies nr is equal to 1 and ms equal to 1. Since equal to Rn, since multiplication is commutative in Z. Which implies n is equal to r is equal to plus or minus 1 and m is equal to s is equal to plus or minus 1. Since n, m, r, s element of Z, all are integers, so n can be either plus or minus 1, these two values. No other values. 1 by n is possible, but the all values belongs to Z, so this value should be plus or minus 1. Therefore, hence 1 1, 1 minus 1, minus 1 1 and minus 1 minus 1 are the units of Z cross Z.